Over the past few videos, I've talked about amino acids, I've talked about protein structure, but I've kind of skipped over or ignored the peptide bond. We're going to remedy that in this video and ask what's so special about peptide bonds. So set the stage, right? Proteins fold to specific structures to do specific jobs. Here I'm showing the protein albumin, which folds to a particular structure that allows it to transport fatty acids in the bloodstream. It can only take on this particular structure because it's made out of amino acids with specific properties. So amino acids, just to remind you, are characterized by having an amine on one side, a carboxylate on the other, and then some R group that determines the identity of that amino acid. When we're building a protein, what we're doing is we're joining these peptides end to end, or we're joining amino acids end to end into peptides by forming peptide bonds. So I'm showing these here in kind of a cartoon schematic fashion where with every reaction or every bond that forms, we're kicking off a water molecule. It turns out this peptide bond is really cool and important. It's more than just, oh, look, it's a random connector. And so what we're going to be asking in this video is what makes it special. And we're going to be thinking about it first more like chemists and then more like structural biologists say that think about protein structure. So let's get into those two features. First, let's just talk about the formation of the bond itself. How is it formed? It's formed by a condensation reaction. So we have a nucleophilic attack, we can do English, by the lone pair on the nitrogen, generating an intermediate. This intermediate can then be resolved by the formation of a water molecule, right? So we formed a new peptide bond. And in the process, we've created a new water. The reverse of this reaction is just a hydrolysis. And so I'm going to draw it in this way, where we have nucleophilic attack on the carbonyl. That, again, generates an intermediate. And now this intermediate is going to resolve, and we are going to generate two individual amino acids, right? We've cleaved the peptide bond, and in the process, we've taken up an entire water molecule. So going in one direction, going in this direction here, we are doing a hydrolysis reaction. We're taking up a water and we're cleaving a bond. And then going in this direction, we're doing a condensation reaction. We're releasing a water molecule and we're forming a bond. Now, I'd like you to think for a second, if you were the master of the universe and you were building proteins from scratch, which way would you want this equilibrium to favor? Would you want this equilibrium to be favored so that the peptide bond would break spontaneously, that it would favor breaking? Or would you want to have it be favoring this direction where the peptide bond would form spontaneously, where it would stay formed? Now, I'm not the master of the universe, but if I was, I would definitely make it so that the peptide bond stays formed, right? If a cell goes to the trouble of building a peptide bond, you'd want that peptide bond to stick around. But interestingly, the opposite is true. The equilibrium actually favors hydrolysis. And it does so. Standard state free energy for this is about 20 kilojoules per mole, or minus 20 kilojoules per mole. So it favors breaking the bond by 20 kilojoules per mole. And if we plug this into an expression for what's the relative probability of breaking versus forming, we get that it's 3,200 to 1 favoring, at standard state, favoring breaking a bond versus forming a bond. I mean, what? Right? That's really confusing. How could that be true? How could this even work where we are taking a protein's building a cell, the cell is building out proteins, it's an array of peptide bonds, and yet it's favorable to break those bonds? To answer that question, we can think about this more like thermodynamicists. And I'd actually like to, if you haven't thought about it already, but think about this. We know the free energy, I'm going to go back a slide. We know that the free energy to break the bond is minus 20, so it's favorable to break it. But what does that tell us about the rate of breaking, right? And so what do we know based on that free energy about the rate at which this bond breaks? So maybe think about that, pause if you need to. We're coming out of a pause, and I'm going to say, what does it tell us about the rate? It doesn't tell us anything, right? And the reason it doesn't tell us anything is because thermodynamics tells us about where the direction is going, but not the rate at which it's going to go there. And it turns out in this case that hydrolysis is very slow. In fact, if you look at the rate constant for that, it's 4 times 10 to the minus 9th per second, so 4 billionths per second, I guess. I don't know what that means practically, so I'm going to translate this into other units. So just imagine we're watching a single peptide bond and we're saying how long is it going to last? On average, the half time for this is 7.9 years. So we'd have to wait about 8 years to see a peptide bond break after it's been formed. So that's pretty good, right? What this means is that the peptide bond is kinetically stable. It sticks around once it's made, right? So a cell might spend some energy, build a peptide bond. Once that peptide bond is built, it's stable for 8 years or so before it's going to break. That raises another question, though, which is, well, why? Like, why is this bond so slow to break? And it turns out the answer is resonance. So the lone pair of nitrogen can pop down here, and we can move electrons up onto the carbonyl. What that does is it creates this pseudo double bond, or this quasi double bond character of the peptide bond. And this has two effects on the rate to break it, to cleave the bond. The first is this carbonyl. Remember, the way that this bond breaks is hydrolysis with a nucleophilic attack at the carbonyl. That carbonyl is simply less accessible because of this resonance form. And second, the amide nitrogen is actually a very poor leaving group. So in order for this bond to break, you have to do two low probability things. You have to get an attack, and you have to get the nitrogen to leave. If those two low probability things happen, sure, the bond breaks, but that just doesn't happen very often, and so it's a slow reaction to do so. Okay, so let's quickly summarize the organic chemistry side of this. First, a peptide bond is a bond that condenses when it forms, it hydrolyzes when it breaks. Equilibrium actually favors hydrolysis by about 3,000 to 1. But the resonance of the bond actually slows down hydrolysis, meaning it's kinetically stable. The bond, once made, basically hangs around, at least as far as the lifetime of, say, a bacterial cell is, that bond is made forever. Okay, there's the chemistry side. What are the structural features of peptide bonds? So one of the interesting things is actually comes straight out of that resonance form. So that resonance form means that the peptide bond can't actually rotate. So the way we normally draw the peptide bond is something like this here, right? Where we've got a single bond attaching the nitrogen to the carbon, and you might look at that and say, oh yeah, that can totally spin around and rotate. But because of this resonance form, this protein peptide bond is actually constrained to be within the plane. In fact, we can actually draw a nice diagram of that. I'm doing it with the pink square here, but I'll actually draw it out here manually. So what you do is you take the C alpha carbon of the I amino acid and the I plus 1 amino acid. So you take each of those. Those are going to be the corners of your plane. And then you draw a box that connects the carbonyl of the I amino acid and the amide proton of the I plus 1 amino acid. And that plane, those bonds are basically stuck in a plane. They can't rotate. It's effectively a double bond character of this bond. And that actually has really important implications for protein structure. So let's unpack those. So first of all, it means that when the peptide backbone is rotating, instead of it flopping everywhere, it's actually constricted. So it can only rotate about these planes. So if you're standing on one of the C alpha carbons, so we're standing on the C alpha and looking to the left or looking to the right, all we can do is rotate planes. We can't rotate in every which way. And what that actually means when we think about the entire chain of an amino acid, an amino acid chain of a protein, we're actually seeing a bunch of planes rotating relative to each other. And that means that instead of being a floppy thing of spaghetti, a polypeptide chain, a protein chain, is actually more like links, right? So you've got a link, and then a link, and then a link, and then a link. Think a bicycle chain compared to spaghetti, right? A bicycle chain can flop, sure, but it's constrained in what it can do because it's made out of links. We can think about proteins and amino acid chains exactly the same way. They have constraints on where they can rotate because of these peptide bonds. And we'll see later that's actually really important for the formation of specific protein structures. Further, the presence of these peptide bonds just constrains what's possible. So now I'm actually showing this with full van der Waals spheres for all of the atoms. So this is a space-filling model. This is about what size the atoms fulfill. We're doing the same moves that we were doing before, where we're rotating those peptide planes. And hopefully what you can see, I'll pause it when we get there, there's some of these rotations that are extraordinarily unfavorable, right? That is just like a huge steric clash. But because you can only rotate in one axis, you have these strong steric clashes. And what that means is just like having the planes themselves, that the chain is strongly constrained. Again, it's not a floppy spaghetti thing. It's more like a bicycle chain. The other thing that this does is it creates alternating patterns of donors and acceptors that are sticking off the side of the chain. So actually, if you're working on your structural reasoning in biochemistry, this is a good point to pause the video and sort of scribble all over your slides if you have them, where are the donors and where are the acceptors. So I'm giving you a chance to pause. Okay, can't say you unpause here. What we have is an acceptor and then a donor, and then an acceptor and then a donor, and then an acceptor and then a donor, right? The acceptors can take a hydrogen from a hydrogen bond. The donors are donating a hydrogen to the hydrogen bond. But donor, acceptor, right? But this is this alternating array of repeating donors and acceptors that are attached to a rigid plane. So why might a rigid plane of donors and acceptors be important for protein structure? Think about that. Why might that be important? Protein secondary structure, right? We talk about alpha helices and beta sheets. Well, what they are is they are repeating hydrogen bond patterns, repeating donor and acceptors that are in specific orientations. And in fact, now if you look at, say, an alpha helix wrapped by these peptide bond pink squares, what hopefully you can see is it's basically like we've wrapped the helix in a wrapping paper or something with these alternating donor-acceptor pairs sticking off the side of it. The reason that's possible is because the peptide bond constrains those donors and acceptors to be in very few orientations. One of the few orientations they can make is an alpha helix. The same is true for the sheet. You'll notice you have these really just sort of straight arrays of corners of these peptide bonds, donors and acceptors. That's where this ordered structure comes from. There are actually researchers that have tried to build non-protein proteins, so take other sorts of organic chemistry molecules and build something that operates like a protein. And it turns out it is very difficult to find atoms, sort of polymers, that will assemble into things like secondary structure because you have to have this beautiful exact match of the donors and acceptors with the rigidity of the bond, with the flexibility of the chain. So it turns out peptides are actually quite good at this structure formation thing, might be why evolution selected them. Okay, so both secondary structures, alpha helices and beta sheets, are stabilized by these planes of donors and acceptors. All right, so let's summarize the structure. Actually, we're going to summarize everything here. So first, the peptide bond is a bond that condenses when it forms, it hydrolyzes when it breaks. Equilibrium favors breaking the bond slightly, but this is kinetically stable, meaning once you form a peptide bond, it is stable because it's just so darn slow to break the bond. The reason it's slow to break the bond is because of this resonance structure that makes it sort of a pseudo double bond character in the middle. That resonance, that double bond character, makes the peptide bond itself planar and rigid, which then creates alternating acceptors and donors across the chain, which then facilitates the formation of particular secondary structures. Okay, that's what I have here. Wrong button. Oh, there's the right button. Okay, I can do this. So yeah, that's what I have for this video. In the next video, we'll actually start finally unpacking why do proteins take a particular structure, and then move on to fun things like protein dynamics. So I look forward to seeing you in those videos.